The next topic in trig transformations is writing trig equations. So we're going to be given a graph, and then we need to write a function rule for that graph. The goal is to recognize one of the 6 trig expressions that we've been talking about, and then apply the proper transformations to that expression in order to map out what is happening on the graph. So fair warning, there are multiple answers for all of these. I am going to be choosing a trig expression that needs the least amount of transformations. So if you end up doing something else, like we could, for this first one, we could use positive cosine, positive sine, or negative sine. So I would suggest if you do it one way and you see that I have an answer for a different way, graph them in Desmos or on a graphing calculator and see if they overlap. So, or plug in a value and see if you get the same output. That's a way to test if our functions are equivalent. All right, so with this one, anytime I see a sinusoidal curve, I'm going to gear towards cosine. And that's just because it's easier to find the maximums, and I'm using that maximum to find the amplitude, and I use the midline to find the amplitude, so it's just an easier way to get everything together quicker. There might be one where sine is more appropriate, but for this one, it's definitely going to be cosine because I see that maximum close to the y-axis, okay? So on this one, I know it's either going to be sine or cosine, and we also have our midline mapped out at -2, which means I know d is going to be -2. So for these equations, we need our ABCs, so A, B, C, and D. So with our midline provided for this curve, we already know that D is going to be -2. And again, you have your little formulas for amplitude and the vertical translation or the midline, but since we have a graph, we can just use it in order to see how far the extrema from the midline. So I'm going to go 1, 2, 3, 4, 5. So this particular maximum, well, all of the maximums are 5 units from the midline. Therefore, our amplitude will be 5. The next one I'm going to look at is the b value. So for the b value, we need the new period. So the period of this transformed function. And again, this is why I use cosine, because I'm going to be using this maximum multiple times. And I can use it for the period as well, because if I look from maximum to maximum, that is going to give me my new period. So if I look at this one, they are 1, 2, 3, 4, 5, 6 units apart, or 6 tick marks, I should say, because this maximum is at -5, this one is at 25, therefore the new period is going to be 30. So for our b value, we'll do old over new. The old period for any sinusoidal curve is going to be 2 pi, and then our new period for this transformed sinusoidal curve is 30, so we end up with pi over 15 as our b value. Now for c, I'm going to use that same maximum again, because I need to see how far did this max shift off of the y-axis. Because if we think about our parent function cosine, the parent function for cosine, which means there are no transformations applied, it has a maximum on the y-axis, right? So I want to see, okay, how far did we shift this maximum from the parent function? And I can see that it is shifted to the left by 5 units, so it's at -5, which means my c value is going to be -5. So in class, I've been flipping back and forth about this. This might change as we go forward. As this course grows, when I made this video, it's in its 3rd year of existence. We've been seeing x plus c within our transformation map and x minus c. I'm going to go ahead and say, let's do c at face value. So whatever we see in the transformation graphically, let's go ahead and apply it. That way, when we plug it into our transformed function, we will have the opposite value show up inside of our function rule. So again, this might change a little bit. It shouldn't. This is what we do for our parent functions for non-trig expressions. So it should align with that, so that way we have some consistency. So now that we have our a, b, c, and d, we can go ahead and write our function rule. So I'm going to do y is equal to, a is 5. I used positive cosine, and then our b value is pi over 15. And then we'll have x minus negative 5, so we have x plus 5, and then minus 2. Now, if you wanted to use sine, then you would use this point, all right? Or this point. You could use either one. It's where the sinusoidal curve is passing through the midline, and it's a point of inflection, and it's increasing, which means you could use positive sine there. Again, you have to do a little bit more work to find that, but you could. Also, it's not exactly on a tick mark, so you would have to make a guess or find it, which is more work than what we did for this maximum here. So that's another reason why I used the maximum, is because it was on an integer. I know exactly what that value is, so I'm not having to find it or guess. So I guess the or could be negative cosine. So you could do y equals negative 5 cosine. Nothing changes except for the phase shift. No matter if you use positive or negative sine or positive or negative cosine, the only thing that will change is the phase shift. So if I were to use negative cosine, I would use this minimum here. This would be my negative cosine. And I see that it is at positive 10. So that means my c value would be negative or positive 10, which means in my function rule, it would be minus 10. So if you were to graph these on a calculator, they would overlap because they are equivalent. All right, this next one. Again, you want to think of your 6 trig expressions, and you want to pick the one where there will be the least amount of transformations applied, just because it's more efficient that way. So with this one, it is increasing, and it looks like tangent. So we're going to use tangent for this one. Now, you could use cotangent, but you would have to look for different attributes because you have to relate it all the way back to its parent function, and we use the y-axis for that, okay? So luckily for tangent, the parent function of tangent looks like this. That point of inflection passes through the origin. So we want to relate, okay, how far did we move that point of inflection off of the origin? Okay, and then I'll even include the vertical asymptotes here. All right, so we chose our parent function, and now from here to write our equation, we need our a, b, c, and d. So I'm going to go with our vertical shift and then our horizontal shift as well, because with that point of inflection for our parent function, it is 0, 0. So we can use this wherever this goes. That will tell you your horizontal shift and your vertical shift, all right, based on that coordinate point. So our coordinate point is moving from 0, 0 from the original, and it's now at 0, 2. So that 2 is telling me that it was shifted up 2, therefore my d value is equal to 2. And then we also use this point of inflection for our phase shift or our horizontal shift. Our parent function is at 0. Therefore, this has no horizontal shift, so that means no phase shift, so c is equal to 0. So that's what's nice about tangent, is that we can use that point of inflection to find your c value and your d value. So c is equal to 0 and d is equal to 2. Again, it's all about relating it back to its parent function and what's being shifted and by how much. So now let's look at the b value. The b value, we need the new period. And for this one, we can look at the asymptotes. So the original period for tangent is pi. But if I look at this one's stretched out by a lot. So if I look in this direction, we go to negative 3 pi over 2. I can think of that, if I just ignore the radians for a second, I can think of that as negative 1.5. And then in this direction, I'm also going to 3 pi over 2. So I can think of that as positive 1.5. If we take both of these distances, we have 1.5 plus 1.5, so that's going to give us 3. And then if we come back to our radians, that means we have a period of 3 pi. So if we think about it, the original period for tangent is pi, now it's 3 pi, so we stretched it out by a scale factor of 3, which means we should get the reciprocal of that for our b value, which would be 1/3. But let's go through the ratio anyway. So the old period for tangent is pi, and then our new period is 3 pi, and we get it, 1/3. A value is going to be a little bit different for tangent. It's not as obvious as our sinusoidal curves, but we can use the outputs for that. So again, those parent functions that we talked about when sketching graphs, if you think about, well, really we're looking at A, so I only care about the y values. If you think about the key points for tangent, we have vertical asymptote, and it's increasing, it's monotonic, it's always increasing, so I have -1, 0, +1. If I go back to my parent function tangent, I can see that my outputs are increasing by 1, +1 actually, okay? And I talked about this in a previous video that you should remember that relationship because this is what we're going to use for writing equations. So we need to see, are the output values increasing by 1? So I want to see, are we increasing by 1 between these two key points? And then do I increase by 1 between these two key points? So if I start from the left, I have 1, and then I have 2, and then I have 3. So that means vertically, this has the same vertical dilation as the parent function, which means a should be equal to 1 because there was no change. If we went from let's say that we went from 1 to 4 to 7 as the outputs, that's a change in 3 units. That means my amplitude, tangent does not have amplitude. That means my a value would be 3. Okay, so that's what we can look at to find the a value, not the amplitude for tangent. All right, so to write this, we'll have y is equal to, our amplitude was 1, so we can just have the invisible 1 there. We'll have tangent. And then our b value is 1/3, our c value is 0, so we can just do x/3, and then +2 for the d value. Now, if we wanted to do this for cotangent, it would be more than just a vertical reflection. We would also have to apply a phase shift in that. So if you see that it's always increasing, just use tangent. It's going to be more efficient for you. All right, number 41. So this one is going to be either cosecant or secant, all right? And my suggestion for this one is to sketch the reciprocal of whatever this looks like, all right? So first, this one doesn't show it clearly. I don't know why they're bolded lines. I need to fix that. Oh, that's the axis, I guess. But there are vertical asymptotes here that we need to remember. So now from here, I'm going to sketch my reciprocal, right? It's going to be a sinusoidal curve. I don't know or care if it's sine or cosine yet, but I just want to see the trends of it. So with those asymptotes, my reciprocal is passing through the x-axis, and then they share those relative extrema. Okay, so I have some sinusoidal curve in here that I can use in order to help determine, okay, what's going to be the most efficient trig expression to use for this. I need to pay attention to the y-axis to make that determination, okay? So I can see that my reciprocal is passing through the origin, which means this would be a great function for sine, since we're using x. If I were to be using the purple curve, I would definitely choose sine because my phase shift would be c equals 0 because it looks exactly like the parent function as it passes through the origin. But since we're using the reciprocal, that means instead of sine x, that means I should use cosecant. That way I'm being efficient and I will not have to use a phase shift for this one, okay? So if we use cosecant, we're going to need our a's, our b's, c's, and our d's. So really what I'm going to do is I'm going to be working more with the sine function to find some of these values, and then also working with the cosecant function. But as far as finding like the the A and the D value, it gets a little confusing because this is a minimum at an output of 4 and then a maximum output of -2. And it's not as familiar as when the maximum is actually greater than the minimum for sine. So in this case, I'm going to be referring to sine a little bit. So if I want to think about that amplitude, the amplitude for sine, all right, not for cosecant, but they will have the same A value. I have a 4 and I have a -2. So if I think about that, I'm going from 4 to -2. I need this full distance, which from 4 to -2, that's going to be 6. And then I want to divide that by 2 to get my amplitude, which will be 3. So my amplitude is going to be +3. So now that I have my amplitude, I know that the midline is going to be that far from the relative extrema. So that means if I have a 4 and a 3, I can do 4 minus 3, which is equal to 1. That's going to be my midline. So D is equal to 1. So the vertical tick marks on this are not really obvious. I'm just going to put it through here. That looks like about +1. All right, so that's how I'm using sine in order to find the A value and the D value for cosecant, okay? So now let's work on the B value. So the B value, we need the new period again. Now the old period for cosecant is the same as sine, which is going to be 2 pi. And then for the new period, we know that we need 3 vertical asymptotes for cosecant. That's how we sketched it before. So with this one, I'm going to start at the y-axis. I see 1, 2, and 3. And with these 3 vertical asymptotes, I can see that we're starting at 0, and we're going to 2 pi. So this is nice. That means there's no change to the period, because the new period is also 2 pi, which means b is equal to 1. Now the C value, I can go back to sine for this. I chose sine because at the origin, it has the same trend that the parent function for sine does, which means the reciprocal will have the same trend. So that means there is no phase shift for this cosecant. Therefore, C is equal to 0. All right, so we have y is equal to, our A value is 3, and I chose cosecant. Our C value is 0, our B value is 1. So that means I'm just going to have my x and then +1 for the D value. Now what we used to teach is that we would always use secant for this, always use secant no matter what. And we said that because this point is sometimes easier to remember to look for, that minimum, okay? But if you use secant for this one, you will have a phase shift, because if you use secant, that means you're thinking about cosine, and cosine has a maximum on the y-axis. So if we were to use secant, we would need to see, okay, how far does this move off of the y-axis? So if you were to use secant, you would have a phase shift of pi over 2. So you could also have y equals, the A value stays the same, the B value stays the same. The only thing that would change is the phase shift, which would be x. We shift it to the right pi over 2, so it's x minus pi over 2, and then +1. So if you graph these two, they will both look like this, okay? And that's because cosecant and secant have the same relationship as their reciprocals, cosine and sine. All right, so this next one, example 42. Again, this is going to be either sine or cosine. My suggestion would be cosine, because I can see that maximum right next to the y-axis, which means it's going to make it easier for me to see 3 of these shifts already, instead of having to fight for the sine, which would, it's not that hard to see if you know where to look, but it's further away, which means it's more work. So let's be efficient. So we're going to use cosine of x. All right, again, we need our A, we need our B, we need our C, and we need our D. All right, so we have our midline passing through. So that means our our midline, which is our D value. Let's see. Okay, so we're going up by 0.1, 0.2, 0.3, which means this is going to be at 0.25. Or you can use 1/4. I like using fractions, so I'm going to go ahead and do fractions. If you want to do decimals, go for it. Up to you. Doesn't matter. As long as it's accurate. And then from here, just like we did before, I can use the midline to find my amplitude. So my amplitude is going to be the space in here. So I'm going from 1/4 to 0.3. Okay, so let's see. So now, well, I guess I should have stayed in decimal land. It'll be easier to find this. So we have 0.3 minus 0.25 divided by 2, which is equal to 0.1 divided by 2, which is equal to, that'll be 1/20th. Oh, so I guess just 0.05. Yeah, so 0.05. So 1/20th or 0.05. So that fraction fun. 0.1 divided by 2 is the same as 1/10 divided by 2. And from there, we want to see, we can multiply with the reciprocal of the denominator. So we get 1/20th, which is also going to be 0.05. I guess I didn't have to go through all of this. Had I stayed with the decimal, I could have done 0.3 minus 2.5, but reviewing fractions is never a bad thing. We could all use a little bit more of that. All right, so with this one, I went ahead, the D value is going to be 1/4, the A value is 1/20th, and now from here, I can use that same maximum, and I can figure out what is the period for this new transformed sinusoidal function. So my left maximum is at -1, my right maximum is at 7. Therefore, the new period is equal to 8. So to get this B value, we have old over new. The old period is 2 pi for any sinusoidal curve, and then we have 8. Therefore, the B value will be pi over 4. For the horizontal shift, the phase shift, my maximum is going in this direction to the left, and it's at -1. So that means C is equal to -1. All right, so for cosine, amplitude is 1/20th. We use cosine because we use that maximum. B value is pi over 4. And then x minus, we're subtracting the C value, so we get x minus -1, so x plus 1, and then plus 1/4 for the midline. Now, if you did want to use sine, you would use this point here. Or I guess you could use this one as well. But it's where sine is crossing the midline and it's increasing through the midline. So we could use that to write a function rule for sine. So this point is at 5. So C would equal 5. So we could have y equals 1/20, positive sign. So let me do that color. There we go. That way we can see what's changing when we use sine. And then instead of x plus 1, because we went to the left for cosine, we'll have x minus 5, because we're going to the right 5 for sine. There we go. So both of these, if you were to graph these, they would both look like this sinusoidal curve. All right, 43. So now the question at the beginning is, what's going to be more efficient for me to use? We're more comfortable with tangent, but this one is decreasing, and you could use tangent, but you would end up using a negative because you would have to use that vertical reflection. So we're going to go ahead and use cotangent. So again, you can use tangent for this, but I also want to talk about what to look for when you're writing an equation for cotangent. So for cotangent, if you think about the parent function, tangent passes through the origin, which means cotangent will have a vertical asymptote there. Tangent is always increasing, which means cotangent will always be decreasing. And then tangent has a vertical asymptote at pi over 2. Therefore, cotangent will pass the x-axis at pi over 2. All right, so for cotangent, we can still use that point of inflection, but you have to be careful with how you use it, all right? Because for cotangent, the focus now is that vertical asymptote on the y-axis, okay? We can use the POI for the d value for your vertical shift up or down, okay? Because cotangent still has it on x equals 0. I'm sorry, y equals 0. So if we look at this, again, we need our A, B, C, and D. We can see that we are shifting this point of inflection up. It looks like 1, 2, 3 by 3 units. So that means D is equal to 3. All right, next I want to look at I guess we can look at the key points, right? So they weren't really, we'll always label it for you on your assessments. You won't have to guess where they are. So if I look at the key points, this one is at 0, 4. This one is at pi over 4, 3. And then this one is at pi over 2. It looks like it's 2. So what we talked about before with tangent was that it's going up. It was -1, 0, 1. So it goes up by 1 because it's increasing. For cotangent, it should be going down because it's decreasing. So we should see those outputs with those key points go down by 1. So I have 4, 3, 2. So they are decreasing by 1, which means that our A value is going to be 1. Again, if we had something like 4, 0, -4, the output values would have a distance of 4 between them, which means your A value would be 4 for that vertical stretch with a scale factor of 4. But that's not the case. Okay, let's look at the C value. So this is where it's different than tangent. For cotangent, you need to look for that vertical asymptote at x equals 0. Okay, that's going to be what you use for your C value. So I see that there's no vertical asymptote on the y-axis, but there is one over here in this direction, okay? So this vertical asymptote is at pi over 4. So that's what I'm going to use as my phase shift for this cotangent function, because I need to see, okay, how far are we shifting away from the parent function of cotangent, and we use that vertical asymptote on the y-axis. So whenever you're writing an equation, you always revert back to the parent function, and what part of it is on the y-axis, that's going to determine your phase shift. So with this one, our C value will be -pi over 4 because that vertical asymptote is to the left. For the B value, this will be the same. We're going from vertical asymptote to vertical asymptote. So we need the new period to find that B value. So if we look in this direction, we have -1/4. And then in this direction, we have +3/4. They're in radians, but it's fine. So I have 1/4 plus 3/4. We have 1. So the new period is just pi. This is the same as the old period. So we'll have pi over pi, which is equal to 1. So no change with the period. All right, so y is equal to A is 1. We're using cotangent. Our B value is 1, which we can leave that alone. And then we have x. And then we have -pi over 4 for C, which means we'll subtract that, so it becomes a plus. And then our D value is 3. All right, here is the last one, example 44. So if we look at this, it's either going to be cosecant or secant, right? So again, my suggestion is to sketch what's happening in between. So it looks like it's going to pass through. It's lifted up, obviously, so I'm going to try my best to get a sketch in the middle here. All right, again, to make this determination, my focus should be at the y-axis to decide which function to use. So if I look at the y-axis, I sketched in the reciprocal, so it's either, we can use sine or cosine and then use its reciprocal for this. But if I look, I notice that I have a maximum for that reciprocal on the y-axis. So what function should you think of for that? Well, that should be cosine, because cosine also has a maximum that passes through the y-axis. So it would be more efficient to use cosine x for this one. Oops. I say cosine, but we want to use the reciprocal, which is secant. All right, and I choose that because now I don't have to worry about a phase shift. All right, so our c value will be equal to 0. Again, determining which function to use, it comes from knowing your parent functions, not just 2 of them, but all 6 of them, okay, and understanding how the reciprocals relate to each other. Okay, so with this one, let's go ahead and find the a and the d value. So for this one, I'm going to use the outputs that are provided for those relative extrema. So as a side note, I can see that it's a relative minimum, but it's a higher output. So I can see I have 4, and then my relative maximum is going to be at 2. So these have a distance of 2, right? And if I divide that by 2, I end up with my amplitude. And in between these two, splitting that in half, that's going to tell me the location of my midline, which will be at 3. So d is equal to 3. The midline for cosine. Next is the b value. This one isn't labeled that well either, but we can figure out what it is because it's equal length input value intervals. So I'm at 0, and then I have pi over 2, which means this is pi over 4. This is 3 pi over 4. And then this is negative pi over 4, so increments of 1/4. So again, a full period for secant and cosecant, they have 3 vertical asymptotes. So on this side from the y-axis, I have a 1/4. And then on this side, I have 3/4. Add those together, that means the new period is 1. And then we are in radians, so it's going to just be pi, so 1 pi. So old period for secant is the same as cosine, which is 2 pi. And then our new period is pi, so our b value is 2. So we have y is equal to secant. Our a value is 1, our b value is 2, and then our d value is 3. Again, this can be written as cosecant, but you would have to use this vertical asymptote as a phase shift. All right, but we chose secant because it was more convenient. All right, hope this helps.